So worksheet 127, number 3, is asking us if the conditions for the intermediate value theorem hold true for this function on this interval, and if they do hold true, find the c that will give us this k value. So first off, our function is not continuous. However, our function has a discontinuity at 2. Let's do this in blue. A discontinuity at x equals 2. So we can say f of x is continuous on the interval 3, 5. And so we find the value of f of 3, which is equal to 1 over 3 minus 2, that's 1. And we find the value of f of 5, which if we find that, that's 1 over 5 minus 2, which is 1/3. And we find that those two values, 5/6 is between those two values. So by the intermediate value theorem, all conditions are met. The function is continuous, and k is located between the y-coordinate of our two endpoints. So because those conditions are true, we can find a c that satisfies that. So we're going to find what is the c. So what f of c equals 5/6. So what we can say is 1 over c minus 2 equals 5/6. And if we go about solving that algebraically, we can cross multiply and get c equals 5c minus 10. And doing a little bit more, sliding things around to make room, we get 16 equals 5c, or 16 over 5 is c. So this is the c value which would satisfy this statement. Problems 1 and 2 are similar in vein, and we can attack them in very much the same way. It does ask us to sketch a curve, so very roughly, I don't have a graph here, but this curve has a vertical asymptote at 2, so our curve looks something like this. We are interested in the interval from 3 to 5, and we're interested in a k value of 5/6. So that means the intersection point occurs at 16 over 5, which is just beyond 3. 16 over 5. Number 5 asks us to show that the function g of t, which is equal to t over t plus 1 on the interval of 0 to 1, takes on a value of 0.499. So when we look at this function g of t, we have to ask ourselves if the function is continuous, and the only discontinuity that exists for this function is when the denominator equals 0, and that's at -1. So we are continuous on the interval 0 to 1. So the conditions for the intermediate value theorem hold true. So you could say g of t is continuous on 0, 1. Furthermore, we can figure out that g of 0 is 0 and g of 1 is 1/2, and 0.499 is between those two values. So by the IVT, we know that that graph at some point takes on the value of 0.499. The question doesn't ask us to find what that value is, but we could, much in the same fashion as we did for problems 1, 2, and 3. All right, question 8 we're going to approach in the same way, and what we have to do is show that there is a root on the interval. And so what it means by show that there is a root, it means if you take the function and set it equal to 0, there is some x value that will satisfy this equation. So the first thing we have to do is establish if this function is continuous, and cosine is continuous everywhere and minus x is continuous everywhere, so this function is continuous everywhere. So we can say that we have continuity on this window. So the conditions of IVT are met. Cosine of x minus x is continuous on 0, pi over 2. So now what we need to do is evaluate our endpoints, and f of 0 is, let's see, cosine of 0 is 1, so we have 1 minus 0, or 1. And f of pi over 2 is, let's see, cosine of pi over 2 is 0 minus pi over 2, which is negative pi over 2. So we know that this is true, that there is some value of 0 between those 2 points. So because there's some value of 0, we know that this function has a root by the IVT. And again, the question just says show that the root exists. So at this point we have basically shown it. So there exists a c such that f of c equals 0. Alright, so looking at problem number 10, which I talked briefly about in class, what we have is a scenario where we have a runner, Jesse, who at the start of the race, after 1 minute, Jesse is going 20 kilometers per hour, and after 3 minutes, Jesse is going 17 kilometers per hour. And it's possible that maybe his speed was modeled by this curve, or perhaps his speed is modeled by this curve. We really don't know what shape that curve takes. It could take anything. And we have the same thing going on for the runner K. At the first minute, K is running at 15 kilometers per hour, and at the third minute, K is running at 19 kilometers per hour. And maybe K speeds way up and then kind of stays steady, or maybe it's a slow, gradual climb to the speed of 19 kilometers per hour. The point is, when we look at this visually, we can see that there is a point, maybe it's here, or maybe there's a different path and it was this one or this one, but there's a point where both runners are running at the same speed. And we don't know what that value is, so we're going to call that value K. And what we can say is, I am interested in this K. I'm going to set up an inequality that says, let's shrink this down, that says that 15 is less than 17, which is less than K, which is less than 19, which is less than 20. So there has to be a K, some K value, that is trapped between 17 and 19. And it's guaranteed that at some point both runners will travel that at that speed, because we have one runner who's going from 15 to 19, and the K is between those values. And then we have another runner who is going from 20 to 17, and the K is between those values. So we can use the intermediate value theorem to prove that this k exists. And here's how we do it. Let's take this thing and shrink it down over here. Okay. Since j of t is a continuous function on the interval 1, 3, and f of 3 is less than k is less than f of 1, there exists a c in the interval 1 to 3 such that f of c equals k. And that's the scenario that we have for the runner Jesse. And we can create the exact same scenario for the runner K. And we'd write that since k of t, we'll call k for k, is continuous on 1, 3, and f of 1 is less than k is less than f of 3, there exists a c in 1, 3 such that k of c equals k. And in retrospect, maybe calling the function k was a little bit misleading because this k is our black k, not our function k. So don't confuse this k with this k. Different values. Now that we've established that a k exists, the second part of the question is, can we tell where that k exists? And the truth is, no, we cannot. And we can look back at our diagram and see we have lots of different scenarios. Maybe our k exists at 1.2 seconds, or maybe our k exists at 2.8 seconds. There's no way with the information that we have to tell for certain where that k exists.